Wait for the drop!
I had complaints that my hand was getting in the way. So instead, I decided to do it this way. Once again, recording this on a very hot day. Seems to be a pattern when you have a CT. We have nice weather. Who knew? So, question number 1. The water in this pan is boiling. That's this way on the camera. State the temperature of the boiling water. Well, that's sort of a fact, general knowledge question, that one. Water boils at 100 degrees Celsius. If you put the little O, the degree sign, that could be an angle. So it didn't carry the mark. You needed to write 100 either degrees Celsius or that little 0 symbol, degrees, and a C. Either of those. 1 mark for the 100, 1 mark for degrees Celsius. The main part of the pan is made of metal and the handle is made of wood. Why is the pan made of metal? Metal's a good conductor of heat. It's an insulator of heat, good conductor of electricity, and a good insulator of electricity. Now, multiple choices are kind of cool because you get 2 that are definitely wrong. One is maybe right and one is definitely right. So 2 that are definitely wrong is we're not doing electricity right now. So this question is not talking about electricity. Take out C and D. Metal's a good insulator of heat, doesn't let heat through, or a good conductor of heat, does let heat through. Metal is a good conductor of heat. It's one of the properties of metals. That's why we make pans out of metal. Moving on. Name one other material that could be used to make a handle that is safe to use. So look at these. Look at these. There. Look at these. The handles here, you've got lots of different types. It was the answer scheme, or the mark scheme, said anything that's a solid insulator of heat. So you could have had plastic. Some people put rubber. Some people put wood, silicon, Bakelite. Bakelite is a very hard, old-fashioned thermoset plastic. There's all sorts, but as long as it was an insulator and it was solid, that was reasonable. You got the mark. What's next? Give one reason why condensation is a physical change. All right, so question 2. Turn the page to question 2. Why is condensation a physical change? Well, what's the difference between a chemical reaction and a physical change? Chemical reactions produce new substances. It's difficult to reverse. That's the property of them. If you get condensation, so on a glass or where you get vapor, water vapor, turning into water the liquid, then of course it's not the same, is it? You could just re-evaporate it. So it's just a physical change. Why? Well, let's have a look. A new substance is not formed. You're not making new. It's still water. That's why it's a mark for that. Why is combustion of hydrogen a chemical change then? Same idea. It's difficult to put it back. Look at this guy. He's exploding hydrogen. This side. He's exploding hydrogen. He's at a Royal Society of Chemistry display, and that is that's going to make water now. First of all, it makes a new substance. Is it easy to unexplode that? It's not quite the same as condensation, is it? Everybody got this right. State whether the pairs of magnets will attract or repel each other. Probably because you're sitting trying to put them together like that. It doesn't work. Write either attract or repel under each pair of magnets. Easy. South to south, repel. South to north, attract. Well, opposites attract is a good way of remembering it. North-north would also repel, by the way. Here is a drawing of a bar magnet. On the diagram, draw the magnetic field around a bar magnet. My gosh, did I get some exciting and interesting shapes. It was hard to remember. Let's put a picture up. There we go. 4. This is the correct idea. You want the shapes where it goes out of the north and into the south. That shape got you the mark, but also the arrows showing that the field lines going to the south is the other mark. So there's 2 marks available for that. Contains a small bar magnet. Explain why a compass contains a magnet. This is tricky. Well, think about it. Why would you put a compass containing a magnet? Why would you have that? It's simple. It lines up with the Earth's magnetic field. It's about remembering that the Earth itself has its own magnetic field. It has gravitational fields as well. We're not talking about gravity today, though. This is about magnets, and magnetic fields are going to interact with magnetic fields. So it lines up with the Earth's magnetic field for 1 mark. The north pole of the magnet is attracted to the Earth's south magnetic pole. 2 marks. So the idea that the poles align is all you needed for the 2nd mark. Something about pointing north, seeking north, that sort of thing. And it lines up with the Earth's magnetic field are the 2 parts to the answer. Question number 4, turn the page. The pie chart shows the different types of bacteria found in 3 different parts of one person's body. So you've got scalp, nose, and underarm. So under somebody's arm. And we've got 3 types of bacteria. What does the pie chart of the scalp show? Just the scalp. Okay, let's have a look. The scalp has got only 2 types of bacteria. Notice the nose and underarm have got 3. That stands out to me. And that's what you could say. You could say a named bacteria is in majority or names in minority. But this is really what we're looking at. 2 types compared to 3. What percentage of underarm bacteria were Campylobacter? Let's look at the graph. Then it said suggested area inside the body where you'd expect to find bacteria and many bacteria decomposers. What a decomposer does. So it's sort of all about bacteria being decomposers, where you find them, what proportion are they, all the different types. So looking at the graph, this looks to me like 25%. It's a quarter, isn't it? You see, it's a quarter. So 25% is the mark. Inside the body, you could have had anywhere that's inside the body always has bacteria kicking around. So you've got huge numbers of bacteria. Anything reasonable inside, up your nose, in your mouth, in any part of your digestive system would have been absolutely fine. The intestine carries a large number of bacteria, though. That's the safest bet. That's the one I went with. And it says many bacteria decomposers. Describe what a decomposer does. It breaks down or feeds on dead organisms. They're decomposers. So they've got to be dead. You can get bacteria that do eat live tissue and it's horrible, but actually it breaks down and feeds on dead organisms is the one that we're talking about. A drawing shows a compass. Look, I put a compass in. It's pretty handy. In north, south, east, or west, and it said choose from north, south, east, or west. I grant you, it's not completely north. If it were completely north, it would be straight up, and I got sort of north, northeast, and yeah, that's fine. But north, choose from north, south, east, or west. There were your options. Then it said explain your answer to A. Why is it? Now, I see what you're saying when you put because it's pointing upwards. I get that. That wasn't really what we're looking for there. The compass is then placed next to a magnet. Magnet's going to have a significantly stronger magnetic field, isn't it? Explain why the compass needle is pointing in a different direction. Well, the answer for this is it's nearest north, so I'm going to pick north. Explain your answer. The Earth has a magnetic field, remember? And what does that do? It makes the compass point north. That's what it was after. Why? It's not that, well, because it's pointing upwards. Yeah, it is pointing upwards. But why is it pointing upwards? Explain. It's the science. Whenever you see explain, it says what's the science. And it says the compass is placed next to the magnet as shown in the diagram. Explain that the compass needle is pointing in a different direction. The magnetic field, or the north pole of the bar magnet, is attracting it. Because the magnetic field you're putting it now is now the stronger one. So it's overcoming the magnetic field of the Earth, and it's now attracted to the north of the bar magnet instead. Next question, number 6, Maddie and what does that say, Lilia. Making bread. Oh, okay. Two different types of dough. They put the amount of each dough mixture into two separate measuring cylinders and put the measuring cylinders in a warm place. The table shows their results. So we've got dough A, 100 grams of flour, 5 grams of sugar, 3.5 grams of yeast, and 120 cubic centimeters of water. Starting volume was 30 cubic centimeters. Finishing volume was 55 cubic centimeters. Okay. Dough B had 100 grams of flour, 10 grams of sugar, 3.5 grams of yeast, and 120 cubic centimeters of water, centimeters cubed of water. 20 to 50. Okay. Which variable did Maddie and Lilia change? Was it the mass of the flour, the mass of the sugar, the mass of the yeast, and the volume of the water? And explain which dough was better at rising. And some of you fell into the trap with this one. Let's have a look. Which variable did they change? The mass of the sugar. Because everything else, if I look at those numbers, were the same. Most people got that. Which dough is better? Explain it. Remember, explain means use science. And in this case, dough B technically is better. If you answered A, look again. It's because if you take 50 from 20, you get 30 cubic centimeter rise, whereas dough A went from 55 and you take 30 cubic centimeters, you only get a rise of 25. So actually you get a bigger rise from dough B. Think about it. Why does the dough rise? Well, is it the sugar produces gas? No. The flour produces carbon dioxide? No. The yeast produces oxygen gas? No, yeast consumes oxygen. The yeast produces carbon dioxide? Yes. Yes, that's what it is. Look at this on some dough here. Fantastic picture. We've got the yeast produces carbon dioxide gas. It's the only thing. You get these bubbles, and it's those bubbles that make it rise. It's what you need the yeast there for in the first place. The diagram shows, no, turn the page. The diagram shows someone inhaling air. Okay. How does organ A protect from damage if the person falls over? How is organ A protected? So this is kind of assuming that the rib cage is going all the way across and there's a cutaway section. That did cause some confusion. But yeah, let's look at it. You ended up with a rib cage. That was the answer. Describe how person breathes in. Look at the diagram. This was so difficult. If you didn't have a chance, do go back. Pause the video if you didn't write the word ribs on the previous question. Describe how the person breathes in. Okay. Not describe that the air goes up the nose and moves into the lungs. How? How come? How come? How does it go in? Think about it. The diaphragm. That muscle contracts, it flattens and moves down. So that's going to do that. The intercostal muscles, they're the ones between the ribs. Do you remember? The ones between the ribs. They contract and it moves the chest up and out. So what we've done is we've got a volume increase. That reduces the pressure inside the lungs. Air rushes in through the nose and mouth. So the volume increases. So you could have had 1, 2, 3, 4, 5 potential marks for those 3 marks. Diaphragm contracts, flattens and moves down, intercostal muscles contract, rib cage moves up and out, volume increases. That's how the air moves. Read the question again. What happens in the body so that the person breathes in? So that a person breathes in. That's the difference. Okay, so we had to draw lines. Question 8. Draw lines to link each of the words on the left with its meaning shown on the right. Combustion, fuel, hydrocarbon, oxidation. One tricky word in there that you may not have come across, hydrocarbon. You may have to apply some science knowledge there. Hydrogen, carbon. That's what it sounds like. Let's look at the answers. All right, let's get my little pen. I think I've got a whizzy pen here. Combustion, a reaction where burning happens. There we go. Fuel, a substance containing stored energy that can be released during burning. Hydrocarbon, hydrogen and carbon, a substance made up of only hydrogen and carbon. Oxidation, a reaction where a substance combines with oxygen. Okay, there we go. Got it. Did it? Very good. Question number 9. The distance time graph shows Obi's cycle ride. Oh, it's got Obi going on a bike. Which part of the graph shows the fastest speed? Distance time graphs. Write down the correct letter and then explain your answer. Okay, explain. Put some science behind it. Let's have a go. So if you look at the graph going up that side, which will be this side here, this side here, this side here, you'll see that it's got the steepest gradient. The steep gradient is what gives you the fastest speed. So W has got the steepest gradient, it's going up at the steepest angle. And the explanation, because it shows the greatest distance traveled per minute. Or it was steeper. You could have just said it was steeper. You still would have got the mark. Danny takes a can of lemonade from the fridge and puts the can on the table. Explain the direction of energy transfer between the can and the air in the room. Energy transfer. So heat goes from an area where it is to where it's not. So it goes from hot to cold. Cold is just the absence of hot. So it's absence of heat, and it's going to go in that direction. It's called thermodynamics. Here's a cool picture. Look, graphic. I made that all by myself. There it is. You've got heat going into the can because the heat is outside the can. It's in the fridge, so it's taken all the heat out of it, and it is colder. So that's why. And then Danny leaves a can of lemonade in the kitchen table for 6 hours. What happens to the temperature of the lemonade after 6 hours? So suggest what the temperature of the lemonade will be after 6 hours. We're looking for room temperature, any reasonable value around 20 degrees Celsius. It was recorded on an extremely hot summer's day. I get it. You could have put up to 25, 26 in the house. My house was 26.6 this morning, so I get it. But it was. I take the context of when it was being, but 20 degrees is the official temperature of room temperature. Sometimes 25 as well. So you've got a bit of leeway in your marking, as long as it was a reasonable number. Looking at the mark scheme. So temperature, nothing to do with bubbles, nothing to do with fizzy. Temperature, energy, thermal energy movement from the air in the room into the can, because the air is warmer than the can, is the answer for A. For B, the same as the air temperature, or any temperature between 18 and 22 degrees is the official mark scheme. It was recorded in the summer. You did your test in the summer, so I get why you did your temperature that you did. As long as it was a reasonable number of room temperature, that would have got you the mark. So that's a rule of thermodynamics. I think it's the first rule. I think it is. It's definitely one of the rules where energy flows from where it is to where it isn't. You just got to remember that for question 10. Oh, an easy 6 marker. Look at this. Explain the roles of the different nutrient groups in the human body. So let's have a go. Let's go through it. Ta-da. Carbohydrates are the body's main source of energy. They're broken down into glucose, which is used in respiration to release energy for cells. Yes. Fats, an energy store, and can be used for energy when needed. They also provide insulation to help keep the body warm. Used to make hormones. Could have got a mark for any of those. Fiber, sometimes called roughage, adds bulk to food and helps to move it through the alimentary canal. Now, you could have said the digestive system or the guts. That's fine. Through by peristalsis, which I think you did before October half term. This aids digestion and helps to prevent constipation. Very unpleasant because food doesn't move through the gut efficiently, leading effectively to a type of blockage. And vitamins and minerals in small amounts for good health. They do not provide energy but are needed for many chemical reactions to allow cells to work properly. And protein, the famous protein used for growth and repair. I always say growth and repair. It's also used by enzymes and hormones, hair, nails, all sorts of things. Protein, the building blocks of life. So there are your marks. We had carbohydrates, fats, fiber, vitamins, and protein. So you had 5 food groups that you had to be mentioning. And then what do they do? to get your 6 marks. So if you just listed them, you wouldn't have got all 6 marks. You wouldn't have even got 5 because there's no explanation. You needed to say what they are and explain what they do in the human body. You needed at least 3, I think, to make it sound like, you know, a decent number. But I would have expected carbohydrate, fats, and protein. Fiber, definitely would have mentioned of fiber as well, and vitamins and minerals, possibly. You didn't have to mention all of them, but you did have to do state and explain. Okay, so here's another version of that, just in case you wanted to pause the video and take a look. This is done in continuous prose. So this is a different way of writing the same answer. So if you wanted to, you could look at that as another different approach to the same question. Okay, they heat the other ends of a Bunsen burner and measure the time taken for the pins to fall off. Okay, so here's an experiment where we've got a Bunsen burner, and if you were fortunate, your teacher may have demonstrated a similar experiment to conduction here. State while the pins fall off at the end of the rods, it's held on with wax. Think about that. How the heat energy transferred along the rods. They're rods, they're solids. Think about that. Metal rods. Not always, but that's common. In an investigation, so here are they. Here's the apparatus. Why did the pins fall off? Because the wax melted? That's all they wanted. It wasn't a deep answer. How was the heat energy transferred along the rods? Well, you had convection, conduction, radiation, and reflection. Reflection is definitely not right. Radiation traveling through space, no. Convection requires a fluid. It's not a fluid, they're rods. Conduction's your only option. Conduction. Okay, part C. Student used 3 stop clocks to record each time the pin takes to fall off, shown in the diagram. Here are the 3 stop clocks. Remember this fact, there are 60 seconds in a minute. That's going to be useful in a second. In a second. All right, material. Time to pin to fall off in seconds. Seconds. 60 seconds in a minute. Okay. If you go back, you'll see that yeah, a lot of people didn't convert minutes to seconds. If you had 6 minutes, you had to multiply by 6 and add the 4 seconds on. Okay. 4 minutes, 48. You had the 4 multiplied by 60, gives you 4 times 60, and add the 48 seconds onto that. 10 minutes, 52. 10 minutes, 60 seconds in a minute. 10 times 6, 60. 10 times 60, 600, plus the 52 seconds, 652. Do you see? Write a conclusion for the investigation and give one advantage of heating all the rods at once. That was a tricky question. So 6 times 60 for the 6 minutes and 4 seconds, and then add the 4 seconds is 360 plus the 4 seconds, 364. Then you had 4 times 60 plus 48 seconds gives you 288 seconds. 10 times 60 plus 52 gives you 652 seconds. You could write there's a bit of white space there. You could have done a calculation if you didn't have your calculator. Always bring a calculator to a science exam. Always, 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 always. And a pencil and a ruler. It's always really handy as well as your pen. Write a conclusion. Copper is the best conductor of heat because the pin fell off of its rod the fastest. Look at the number, 4 minutes 48. Now, if you didn't get the table right, you still got the answer there to help you. So luckily, one didn't depend on the other, which is good. Give one advantage of heating all the rods at once. Fair test, fair, but then you need to explain why. Why is it a fair test? Just say because it's a fair test, doesn't get you the mark. Why is it a fair test? It's fair. That's not an answer. Explain one advantage. They all start at the same temperature. They all start at the same temperature. If you heat them all at once, like they're not going to get heated. They won't get any variation. What is it about the fairness that you're interested in? Why is it fair? Because they all start at the same temperature. They all get heated for the same amount of time. I don't know. That's not quite right because they have got time that changes. So all starting at the same temperature is your answer, isn't it? If you say fair test, always explain what is it about the fair test that makes it fair. Okay, Marek gets a coat. Oh, and a hat for cold winter weather. That's nice. Question 13. The coat has a silver-coloured lining and thick padding with air trapped in it. State the type of heat transfer that the silver lining reduces. Silver, shiny. Because the trapped air in the coat's padding reduces heat loss. How? And Merrick's teacher says without his hat, Merrick could lose heat by convection even when there is no wind. Explain how convection can transfer energy away from Merrick's head. Well, hope Merrick's a good scientist, because that's quite a scientific thing to advise someone, isn't it? You don't say you'll get cold even if it's not windy, Merrick. You go, you could still lose heat by convection. I mean, it's good and it might be a good answer, but Merrick needs to understand what that means. State the type of heat transfer the silver reduces. If it's shiny, it's going to be radiation. Infrared radiation. Thermal radiation, that would have worked as well. Describe the air trapping the heat. Well, it stops or reduces conduction. You could have said that it prevents the convection because it can't move anywhere, or you could say that air is an insulator, but air is an insulator or it reduces conduction is what your answer there. Okay, Merrick's teacher says that without his hat, he could lose heat by convection even when there's no wind. Okay, tricky, but doable. Heat from Merrick's head warms the air next to it. The warm air particles move faster and spread further apart. Yeah, we're describing a convection current, aren't we? This makes air less dense, so it rises. Cool air from above means moves down to replace the air, or from the side, moves down to replace the warm air, which has risen up. The warm and cool air, the air moving away sets up a convection current, and this carries energy away from Merrick's head to the surrounding air. All you've done is, instead of your lovely diagram, which you've done, and all of like candles or whatever you've used as your demonstration, Bunsen burners, you're just using somebody's hot head as the hot source of heat, and the air is the fluid that gets heated up and rises up because particles move further apart once they get hot, taking the heat energy with them. So 3 marks. There's about 6 that you could have mentioned, maybe 7 different points you could have mentioned, and you only needed 3 of them. Using particles and particle theory to explain why diffusion happens. Okay, so we're going to look at the next part, and we're going to talk about particles here. Use particle theory to explain why diffusion does not happen in solids. And does diffusion happen faster in liquid or gas? Okay, let's have a look at the answers. Here's some diagrams. Here's your particle model. This is very important. Right, you smell food cooking. The smell is spread by diffusion. Use particle theory. So we're just talking about particles. We would like to get the word particles in the answer, therefore. Moving gas particles have mixed with the smells in the air. Or the smells have mixed with the gas particles in the air. Doesn't matter which way around. As long as you talk about particles mixing, there you go. Use particle theory to explain why diffusion does not happen in solids. They can't move. That's it. Does diffusion happen faster in a liquid or gas? In a gas, the particles move faster than a liquid and a bit further apart as well. So it's A. Yeah. Okay, so we talk about decomposition here. Next page. Many bacteria are decomposers. Question number 15. What do decomposers do? Check one box. Does it break down dead organisms? Does it infect living organisms? Does it do photosynthesis or kills living organisms? And then it says, explain why decomposers are very important in an ecosystem. Okay, right. Well, they break down dead organisms. Tick. Why are decomposers more important? Are important, not more important. Why are they? They remove the dead organisms, and loads of people got this. Well done. If you were one of them, good job. They remove organisms that are dead, animal waste, get rid of it. That's good. The second part, which was hard, is they recycle the nutrients, therefore, making them available for other organisms to use. The second mark is the fact they're actually recycling the nutrients. If you got that, you're a super scientist, and you ended your test very well. Add them up, double check your scores, see how you did. Well done, and I'll see you next time for the next CT review. Take care.
Close the tabs and let the blue light fade. of a different kind. Summer's